Hello and welcome to this video on nucleophilic addition. My name is Kim, and in this video we'll describe the properties and how to prepare an organometallic reagent. Organometallic reagents are used to form new carbon-carbon bonds and is an efficient way of synthesizing complex organic molecules from simple starting reagents. Organometallic reagents are composed in two parts as shown in the name. Organo meaning carbon-based and metallic meaning that it's bound to a metal. Now, in many of the organic chemistry reactions you've considered thus far, we think about how carbons are often bound to functional groups that result in electrons being pulled away from the carbon, so the carbon becomes an electrophile or partially positively charged. This happens in groups like carbonyls and alkyl halides. But what if we bound the carbon to a group that is actually less electronegative than carbon, like the metals on the far left of the periodic table, a group that wants to actually give away their electrons? Then the carbon can function as a nucleophile with lots of electron density. For some of the really reactive organometallic reagents like organolithium, the difference in electronegativity between the carbon and the lithium is so big that we can almost consider it to be ionic rather than covalent. This really emphasizes the fact that we've created a fantastic nucleophile, but we can actually swing too far. Like Baby Bear, we want our nucleophile to be just right, because a good follow-up question would be, can we use metals that have really low electronegativity, like sodium or potassium? Well, we could, but they're such crazy good nucleophiles that it would go back and attack our original starting reagent and form chains, instead of holding back until we add in our next step, which we'll cover in another video. Some of the organometallic reagents you might be familiar with is organolithium, organocuprate, and organomagnesium or Grignard's reagent. The most common organometallic reagent you'll see is Grignard reagent. Grignard reagents are organomagnesium based, formed when you react an alkyl halide and solid magnesium. The halide is typically bromide, chloride, or iodide, but is not fluoride, since fluoride is a poor leaving group and would not be happy to leave to make room for that magnesium. Through a reaction mechanism involving the formation of free radicals, for the purpose of this video, we'll consider the magnesium to be the cream in your Oreo cookie and insert itself in between the alkyl group and the halide. The resulting product, RMGX, can also be rewritten as this, with a negative charge on the carbon and a positive charge on magnesium to emphasize that great nucleophile. Preparation of Grignard's reagents must be completely free from water and other protic solvents, since that nucleophile would be so reactive. If water was around, it would react with the water and become protonated, and we would lose our nucleophilic carbon. Remember, preparation of organic metallics is not the end goal. Creating these fantastic nucleophiles is to ensure that we're able to add the nucleophilic alkyl group to another reactant in a second step, which we'll cover in another video. We're asked to predict the product in the following Grignard reagent preparations. Remember the requirements. We'll need an alkyl halide where the halide is not a fluoride. We need magnesium and an aprotic solvent. In A, we see methyl bromide reacting with magnesium in the presence of THF or tetrahydrofuran, which is an aprotic polar solvent. Just like we saw earlier, the magnesium will insert itself between the alkyl and the halide, forming methyl magnesium bromide, a great Grignard's reagent with a nucleophilic carbon. For part B, we see the same methyl bromide reacting with magnesium in the presence of water, which is a polar protic solvent. Sadly, we will not get Grignard's reagent as a product. In C, ethyl chloride is reacting with magnesium in the presence of diethyl ether, which is a polar aprotic solvent. The product will be the insertion of the magnesium in between the alkyl and the chloride, forming ethyl magnesium chloride, a Grignard's reagent. Finally, with D, we have methyl fluoride and alkyl halide. But remember, our alkyl halide can't have fluoride as its halide, since the fluoride doesn't like to leave. Magnesium can't get between the two, so we have no reaction. Remember that this is in preparation for a great Grignard's reagent that needs that nucleophilic carbon. That nucleophilic carbon will be very useful in future nucleophilic addition reactions.